Hello and welcome to today's lesson on the solar system and orbits, which is part of the space physics topic in GCSE Separate Science physics. So in today's lesson we're going to describe how planets and satellites move in orbits. So if we've been successful and learnt in today's lesson, we should be able to understand why forces act on objects carrying out circular motion, understand what and how orbital speeds can change with different orbits, and finally describe how centripetal forces work. So if we are successful, we'll be looking at 4.8.1.1 our solar system and 4.8.1.3 orbital motion natural and artificial satellites, which are both separate science only parts of the specification. So we've got to consider the concept of circular motion. Now there are many examples of circular motion in space, such as moons orbiting planets, such as planets orbiting stars, and such as stars orbiting around the galactic centre. So to understand the motion of these celestial objects, we must consider the physics of circular motion. Now the most common application of circular motion is the orbit of a planet around a star. So let's consider the motion of the Earth around the Sun. Now technically planets move in an ellipse, which is like a squash circle around stars due to gravitational effects, but we're going to assume that their motion is perfectly circular at GCSE. Now when we look at this particular diagram, you will note that the planet will always have a direction of motion which is tangential to the star. Now as it orbits, the Earth or any planet would therefore change direction as it's moving in a circle. So because it's changing direction, this means its velocity is changing as well, because velocity is a speed with a direction. Now because the velocity is changing, this means that the object is in fact accelerating. We know this from Newton's second law, F equals ma, which notes that if there is an acceleration, there must be a resultant force. And the resultant force which causes this circular motion is called a centripetal force. Now this force always acts towards the centre of the circle or the orbit, as the Earth is constantly being dragged towards the centre of the Sun due to gravity, because there's an attraction there, so we call it a centre-seeking force. Now the centripetal force will produce circular motion because there's another effect there as well as this gravitational force of attraction. So any object such as a planet will want to move in a straight line in the same direction, have the same velocity, unless a resultant force acts on it. We call this idea inertia, and it's from Newton's first law of motion. However, the centripetal force always acts to pull the object towards the centre of the orbit. Now it's important to note that any force which acts perpendicular or at right angles to the motion of an object becomes a centripetal force, which is a very important concept in A-level physics. Now a force which acts perpendicular to an object's path cannot change the speed of the object. The force can only change the direction of the path. This is because the force does not act in the direction of motion. This is because the resultant force is at right angles to the velocity, so it does not cause the object to speed up or to slow down. So we would say that because the resultant force is at right angles to the velocity, no work can be done on the object. So it's important to note that a centripetal force causes acceleration by changing the direction of the object, not by changing the speed. But so we would say a centripetal force causes acceleration by deflection. Now the inertia of the object and the centripetal force acting on the object combine to form the circular path of the object. So the centripetal force provides an acceleration towards the centre of the orbit, whilst inertia prevents the body from falling into the centre. So this actually means that if the centripetal force was removed, for example the Sun disappeared, the object would move in a straight line and it would move in the same direction. It will move off in a tangent. So when objects move in a circle, they are constantly changing velocity as they are changing direction. A change in velocity is an acceleration, and only a resultant force produces an acceleration. Now the category of force which causes a circular motion is called a centripetal force. Now the centripetal force always acts towards the centre of the circle, and so therefore gravitational attraction producing an orbital motion is an example of a centripetal force. And it was this centripetal force principle of physics physics, which allowed Isaac Newton to determine that gravity is the force allowing the planets to orbit the sun. So the only force which allows planets to orbit the sun is the force of gravitational attraction. Now within our solar system there is one star, the sun, plus the 8 planets and the dwarf planets that orbit around the sun. Now natural satellites, which are moons that orbit planets, also form part of the solar system. So we can say that the solar system is all the material that orbits the sun, and these include planets, which are large objects that orbit a star. Now we have 8 planets in our solar system, and they have to be large enough to have cleared their neighbourhoods. This means that their gravity is strong enough to have pulled any nearby objects apart from their natural satellite. You've also got dwarf planets, which are planet-like objects that orbit stars but have an object of similar size in their orbital path. Now we have natural satellites. These are natural objects which orbit planets, and we have artificial satellites. These are human-built objects that orbit planets, normally the Earth. And we've also got things such as asteroids and comets, which are smaller, rocky, icy objects which orbit the sun. Now our solar system is a tiny part of the Milky Way galaxy, so this is a massive collection of billions of stars that are held together by gravitational attraction. Now technically gravitational attraction always happens between two bodies, therefore it's the gravitational attraction between the sun and the planets or the dwarf planets or the comets or the asteroids which holds the solar system together. Now gravitational attraction is always present as the planets are always changing direction, therefore are always accelerating. Now basically the gravitational attraction for all planets always acts towards the centre of the solar system's mass, which is in the core of the sun, as 99.8% of the mass of the solar system is the sun. So all planets are therefore accelerating towards the centre of the solar system. However, inertia means that they follow an orbital path and do not fall inwards. So all the planets accelerate inwards as the gravitational attraction is acting as the centripetal force. Now it's interesting to note that the planets of the solar system tend to orbit on roughly the same plane in space, which is called the ecliptic, and this can be observed in the night sky of the Earth. Now we observe that the outer planets take longer to orbit the sun than we do, with the idea of retrograde motion observations on Earth. So the following diagram shows the position of Mars in the night sky of Earth for every day of a month. Now it appears that Mars moves backwards in the night sky. This is actually because the Earth overtakes Mars on the inside of its orbit. So Mars does not actually move backwards, it's an illusion due to our position in the solar system. This overtake happens as the Earth has less distance to travel and is travelling at a faster orbital speed. Now this is an important idea. The closer an orbiting body is to the centre of the orbit, the stronger the gravitational force is, so this means the faster it travels. So you can say that when the orbital radius decreases, the orbital speed increases. So it means that the Earth, because it's closer to the Sun than Mars, has a higher orbital speed. So we can say that the greater the distance from the centre of an orbit to the object orbiting, the slower the orbital speed of the object. So we can note that when you are further away from the centre of the object, you will have a lower speed, and if you are closer to the centre of the orbit, you will have a higher speed. So for a stable orbit, the radius must change if the speed changes. Now we can understand this from two different key principles in physics, either forces or energy. So we can think of it in terms of forces because the further objects are separated from each other, the smaller the gravitational attraction between them, because the gravitational field is weaker as the field lines are more spread out. So if the gravitational force is lower, the orbital speed exerted by the force is lower, the body travels slower. Or we can also consider it in terms of energy. There are two energy stores in an orbiting body, gravitational potential and kinetic energy stores. Now the total energy in an orbiting body must be constant. Energy can't be created, energy cannot be destroyed. Now the greater the separation between the bodies, the greater the gravitational potential energy. So it means that for the energy to remain constant, the kinetic energy is lower, so therefore the body travels slower. So it's important to note the following. Gravity provides the force that allows planets and satellites, both artificial and natural, to maintain their circular orbits. So for a stable orbit, the radius must change if the speed changes. Now the greater the orbital radius, the slower the orbital speed, and this is because the gravitational force between the objects is lower, or more of the orbiting body's energy is in the potential energy store, not the kinetic energy store. Now, within our solar system there is one star, the Sun, plus 8 planets and the dwarf planets that orbit around the Sun. Natural satellites, the moons that orbit the planets, are also part of the solar system. Now, our solar system is a small part of the Milky Way galaxy, and gravity provides the force that allows planets and satellites to maintain their circular orbits. You should be able to explain and describe the similarities and distinctions between the planets, the moons and artificial satellites, and explain how for circular orbits the force of gravity can lead to change in velocity with unchanged speed, and for a stable orbit the radius must change if the speed changes. So if we've been successful and learnt in today's lesson, we should be able to explain and understand why forces acting on objects carry out circular motion, understand how orbital speeds change with different objects and orbits, and finally describe how centripetal forces work. So hope you've enjoyed today's lesson on the solar system and orbits in the solar system, which is part of GCSE Separate Science Physics in the Space Physics topic. Thank you very much for listening, and as always, have a lovely day.